Okay, let's look at problem 3b in this video. So in problem 3b, what we've been told is that V in is made up of two components. Okay, one is the DC component and another is the AC component. Okay, so let's say this is the AC component of the signal and this is the DC component of the signal. And the question that is asked is, okay, what are the limits on the DC component and the AC component so that this transistor or this circuit behaves like an amplifier? And of course, the answer to that question is uh, the limits are we want the transistor to be working in active mode, okay, and the limits are going to come from there. Okay. So, what was the output that we calculated in the previous slide? What we did was we said V out is equal to VCC plus beta RC divided by RB times 0.7 minus beta RC divided by RB times Vn. Okay, and now what we are saying is, well, this V out is basically the collector voltage, isn't it? It is the collector voltage, and we know what the base voltage is, which is 0.7 volts when this is an active mode. And what we want is we want this junction to be reverse biased, right? We want the base collector junction to be reverse biased. Now, what does that mean? That means that V out has to be greater than VB minus 0.5. And we know VB is 0.7 volts, so this has to be greater than 0.2 volts. So one condition, and we can write the condition if you want, over Vn. So what do we get? So Vn has to be less than, in this case, VCC plus beta RC over RB times 0.7 divided by beta RC over RB, right? Which means that Vin has to be less than VCC times RC divided by beta RB plus 0.7. So that's one condition on V in that we have got. What's the other condition on the other side? Oh, wait a minute. I forgot the 0.2 term here. So minus 0.2. Let's put that. So minus 0.2 divided by beta RC times RB. And this needs to be RB and this needs to be RC. Okay. All right. So that's one condition that we have. So let me write that. And that condition, this condition that we calculated, came from the fact that we don't want our transistor in saturation. Let's think about the other condition. The other condition is that our transistor should not be in cutoff mode. Okay, so to get the condition there, what we need to look at is we take a look at VB and IB, right? So what is IB equal to? So IB is equal to V in minus VB divided by RB, right? And for the voltage here, for the circuit to be in active mode and not in cutoff mode, what do we need? First of all, we need IB should be greater than 0, right? Because if there is no current IB flowing in, then the circuit is in cutoff. So we need V in greater than VB, and we also want VB should be greater than 0.7 volts. So if you combine both these conditions, the condition that you get is V in should be greater than 0.7 volts, right? So this is the condition that we get from the fact that we don't want our transistor to be in cutoff mode. Now we can combine both these conditions and what we get is something like this. So we get V in should be greater than 0.7 volts, and we get V in should be greater than, should be RB times beta RC times VCC minus 0.2 plus 0.7. Okay. Now this V in, we said, was made up of two parts, right? V in and plus V in. Now let's say the AC component of the voltage has an amplitude of A. Okay, so it goes plus minus A. So that's, it goes, the maximum value on the positive side is A, the minimum value on the negative side, or the maximum value on the negative side, is minus A. Okay, in that case we can say V in max is equal to V in, which is just a constant, plus A, and V in min, which is equal to V in, is V in minus A, isn't it? And what we are basically saying, if you combine this equation with this equation, what we are basically saying is V in minus A should be greater than 0.7 volts, right? And V in max should be less than this term here. So RB divided by beta RC, VCC minus 0.2 plus 0.7. Hopefully that makes sense.